Thank you everyone for joining the second of our series of webinars. My name is Andrew Twigg. I work on sales at Chronicle. So today Peter's going to do a webinar around benchmarking and Chronicle Queue. So let me just give a very brief introduction to Peter. He's the CEO of Chronicle and he founded Chronicle in 2013. Over the past 7 years, Peter's been pivotal in growing Chronicle software to become a trusted partner to many global tier 1 banks and hedge funds. And our open source software is downloaded over 17 million times, used across multiple industries from biometric research to gaming. The business has now grown to over 3 million per year with a revenue growth in 2020 set to increase by over 30%. Peter's a Java champion and one of the global leading experts in Java development with the most answers on Stack Overflow, and he's driven the use of Java in low latency, opening up the skills and capabilities required to build the most demanding apps. He continues to research and develop innovative ways to utilize Java. The format today is going to be a presentation by Peter and some live coding. It'll be followed by a Q&A. So if you have any questions during the presentation, just submit them via the Q&A feature or the chat feature in Zoom, and Peter will answer them at the end. So I'll now pass over to you, Peter.
Hello, so this one will be a little bit more demo than the last presentation. I'll be looking at both how we go about benchmarking software, as well as a little demo of some of the low-level aspects of Queue and how we access shared memory between different processes. Our use cases are typically low latency trading systems, although the functionality in them could be used in other industries. We're talking today mostly about Chronicle Queue in terms of the stack, but we'll be making reference to bytes and wire, which Queue are built on top of. Typically, we're looking to support microservices that can handle around in the order of tens of microseconds latency, and that's for the entire microservice itself. So obviously the infrastructure needs to be a small portion of that if possible. And the benchmark we're looking at today can produce this kind of profile. So the point of this is to look at different ways of marshalling the data. In this case, a simple new order single and an execution report, and looking at how long does it typically take and what sort of latency distribution do we get, depending on which technique we use. So when it comes to benchmarking, one of the first things that I ask people to do is to be aware of the jitter that your system has. This is the intrinsic jitter that your system causes on processes that are basically otherwise doing nothing. That is no GCs, no locking, no I/O. All they're doing is trying to run a busy CPU. And so what this does, you can actually Google the source for this. It's called Micro Jitter Sampler. If you Google that, it comes up as the source comes up as the first link. And it's a standalone class, so it's fairly easy to run. And what it does is it just keeps calling nanotime, just keeps calling system nanotime, and it looks for jumps in time of at least 2 microseconds. And it just records in a sort of a histogram how often you get delays of 2 microseconds or more, and just puts it in different buckets depending on how long it is. Now, on a Windows 10 machine, this is the approximate jitter count per hour you get of different sizes of delays. And as you can see, we get delays well into the milliseconds, where the Windows machine is otherwise got free CPU, but for whatever reason just decides to stop your process for milliseconds at a time, before running it again. And as I said, it's got no I/O, no GC, no locking involved. There's only one thread that's doing anything in this process. It's just the OS getting involved in delaying your application. Now, I've tuned a CentOS 7 desktop, which is what I'll be using to demo today. It's the first time I've done a web presentation from Linux, so it seems to be going all right so far. I've even tuning it, I still get some quite measurable jitter, and that I'm getting delays that are around 100 microseconds or so. In an ideal server configuration, you're still looking at delays that are going to be around 40 to 60 microseconds some of the time. To some degree, these are unavoidable because there are certain interrupts you can't turn off, and the BIOS, for example, will also interrupt your CPU, and this is not invisible to the operating system. It will just interrupt your CPUs for short periods of time, but nevertheless, it is measurable. So just a recap of the architecture that we're looking to support, and that is that we have an event source. This goes through a function, and this produces outcomes. This is very easy to test and reproduce, and so we can enjoy rapid development of isolated pieces of functionality. Even if you've got a distributed team, you can work to a common API. What you can also want to do is for more realistic applications. So for this simple case, it's good for gateways for normalizing data. However, when it comes to, say, an order management system, you need to have some state, which is, for example, maintaining the current state of any given order. One way of looking at that in terms of function is now it's a function of not just the latest message, but essentially every message it's ever seen. And these can be chained together to produce more complex systems. Another reason we can do this, and we do have an event source that's persisting. It's always writing, so every piece of information that's passed between the microservices is being recorded to a file. And file systems now are not only getting very fast, you can get systems that are well into the gigabytes per second write speed, but you can also have very high capacity at a relatively reasonable price compared to historical prices. So in this example, this is a 1U server that has half a petabyte and costs around £320 per terabyte, which is an enormous amount of capacity. Obviously, you don't necessarily have to have a complete separate standalone server. You can just put some redundant storage internally in your server. A small number of terabytes is usually enough to run these systems. So we're looking at a demo that we looked at last week, but we're looking at some different classes and use cases for this demo. So it is open source. You can run it yourself and see how it behaves. So some instruction on how to run it. So we have our own benchmark harness, and you might be wondering why not use the standard one that comes, JMH, that comes with it's widely used for Java. And the reason is that we're looking at latency profiles for a given throughput. So we might say the throughput is, we might want to test for 100,000 messages a second and then see what the latency profile is. Another thing is that in our benchmarks, they tend to be multi-threaded. And so the sampling thread may be different to the one that's driving the load. And JMH isn't really designed for that. It's meant to be synchronous return. Another thing we use it for is we may actually record multiple probe points to see how it flows through the system. So we'll report maybe 5 to 10 different timing points, and we can see what the delta is for each stage. That's another thing that JMH is not really designed for. It just gives you one set of numbers for an end-to-end. So here's an example of, so this is from the benchmarking code. So we're benchmarking a sample OMS, and this is what the raw code looks like. In our services framework, we have much more complex examples, which are entirely driven by configuration. You don't need to write code to do it. But for the purpose of this benchmark, we've just got a very simple example. So we've written the code for it. And essentially, it just opens up the input queue and the output queue. Then it wraps the output with what's called a method writer. So essentially, it's every method call you make gets written as a message. And you also have a method reader, which does the same thing. Every message message type is essentially the method call that gets turned into, and the DTO or DTOs associated with that message are turned into the arguments. So it's like an asynchronous RMI. It lends itself to a very simple testing and programming model to use this approach. So this is a configuration for JLBH, where we can fiddle with things like this, change the throughput, how long does it run for, whether we want to account for a coordinated mission or not, which is another thing that JMH doesn't really do. So here's with some benchmarks showing what it can happen under load. So this is running through a single thread, and we're the first line we do is starting at 100,000 messages a second, and we show what happens as we ramp them up. The reason it's sort of going in jumps is that what I did is I actually did a much broader sample, but only included the lines where there was a sort of significant step change. So there is a step change between 400,000 and 1 million messages a second, but in between, it doesn't make a lot of difference. And so this machine could handle, for this type of message, 1.6 million messages per second through a single thread. And obviously for every message in, it's also writing a message out. So there's some other products we have that are commercial for improving the performance further, and then we'll get on to the demos. So the first demo is running the benchmark. So one of the things that we do, there's a couple of things that are worth mentioning that we do before running a benchmark, is first to check how is the kernel being configured. So on Linux, that's fairly easy. You just print out the command line, and the two things that we're looking for are whether the C states have been turned off, and also whether Spectre my name's gone blank, mine's gone blank as the other patch, but turning off the patches which were designed to increase security between threads, but unfortunately hurt performance. So we try and optimize the kernel for performance, and we also isolate some CPUs. The reason we want them isolated is, as we mentioned, we want to avoid the scheduler getting involved at all with the CPU to minimize jitter. And if we can, so we can now run the benchmark and see what that looks like. I forgot to mention the other thing that we do is we set the CPUs, the CPU power to be maximum, to maximize it. So you can see here that I've set it to the governor to performance. Typically it's power save by default. And I've tried to set the frequency range to the maximum of the turbo boost. In reality, this is a sort of a desktop PC, and it has limited control in reality. So even though it's got that hint, you can see that the actual speed is 4 gigahertz right now, which isn't too bad since the rated speed is 3.6. So, but obviously you want that to be as high as possible. Now, in terms of the results, we've got multiple runs here, and you can see that the 50th percentile is around 1.1 microseconds. Now, so what is this benchmark doing? Well, it's the time it takes to write a message to the queue, pick up that message in another thread, decode the message, then write another message to the output queue, and then read the message from the output queue. So this is 2 hops of writing first a new order single, and then the reply is basically an execution report, which is a rejection of that new order single. So this is 2 hops, and this is using, of the 4 options for how you lay out your DTOs, this is using the least efficient, but the most flexible from a schema management point of view, so in terms of handling schema changes. And part of the reason I've left it this way because it makes demoing some of the other things I'm about to show you easier. There are options for making what you write more low level, less self-describing, and thus more efficient. But I generally encourage you not to go down that route too early in your development cycle. You should really only do that once you've got a pretty stable system that works and you just want to optimize it, make it go a bit faster. And in fact, that's the purpose of this chart that I had earlier, is to show you how much difference the different options make. So you can see that the typical is about 1.1, as I just saw. There's a way of doing pre-generating the code that's doing the serialization rather than having it do it automatically. That's more efficient, but obviously you have to regenerate that code every time you change the DTO. Then there's a lower level format which is not self-describing. Instead of writing out what the data is plus what it means, it just writes out the raw bytes, and that produces a more consistent result, particularly in the high percentiles, but is the hardest to work with in terms of schema changes. The self-describing messages, for example, the fields can change order, they can change type, you can add a field, you can remove a field, and it will handle it all for you. In the raw format, that you're somewhat left on your own to do that. We have a technique to make that a bit more manageable, but now you're having to think about, well, what is the impact of adding a field? How do I manage that? Which is nicer if you can just avoid that. So if we go to the next demo. So the next thing I'm going to demo is, so I've shown you the performance and how we measure it and why we measure it that way. I've also shown you how we optimize the kernel, or the two key things to look at in terms of optimizing the kernel, and it's that reducing that jitter is a lot of the reason for that tuning, particularly the isolated CPUs, makes an enormous difference. The affinity library that we use actually works on Windows, but without the isolated CPUs, you don't actually see any real benefit in reality. So it's the combination of isolating the CPUs and assigning the CPUs to those critical CPU threads to those CPUs. So this is another example which I've only just added. And what this is doing is showing what happens when what is actually happening in the queue itself, what's happening under the bonnet. So we've got a simple program that all it does is that every time you hit return, it goes and adds a new order single. So in this case, I'm sending a new order single to the queue itself, which is in here, and I'm also doing, so you've got the ability to just mock method calls and then just write to system out what that method call was. That way is a simple way of logging what it is that we're writing to the queue as we write it. And then we've got a viewer, all its job is to read the queue, and everything it reads from the queue, it also is writing to a mocker, which just, whatever method calls get called on it, it logs them. So if I run the adder now, and the viewer. So in this case, I'm actually running the program using Maven to trigger these programs. Part of the reason I'm doing that is that IntelliJ doesn't allow you to see the output of more than one program at the same time, or at least I couldn't figure out how to do that. So I'm using these two to trigger and watch the queue, while I have another tool which will dump the contents of what's in the queue. So this queue dump main is actually part of queue itself. The only thing you need to specify is the queue you want to read. And if I run it, the moment you can see, this is what the low-level dump of what is in the queue. So the queue has a special file called a store, and that table store has records of all the information for that queue for the life of all of the roles. So that file stays there, and it has meta information which you can see, like you know, what is the highest and lowest cycle, which of course there isn't any yet, a value for locking, and you know, modification count. So, but the key part is recording things like what is the role cycle that the queue will use, and what its intrinsic source ID. That's used for tracing messages as they pass between the queues. So say I add a message to the queue just by hitting enter. You can see that this is the method call that was made. This is how it looks when it dumps out that method call. And the interesting thing, especially, I don't know if you remember from the last session, is that in the DTOs themselves, we are actually storing things like the sender, target, and sending time as longs. That's to reduce the memory footprint and the overhead of managing those values. So we can do comparisons and copies of those values without, with very little overhead compared to managing an object that might have. So for example, a string has a reference to an object which internally has an array. So if you want to compare those two strings, if they're equal, it has to go through each byte individually within the array to compare them and make sure that they are the same. In this case, if you've got a long and you want to do a long comparison, that's actually just two register comparisons. It's as lightweight as you can get in terms of comparisons. So, so there's some benefits in terms of efficiency. Where this gets interesting is that if we look at the raw queue, we can see what the data actually looks like. So we can see now that there is now a store that has a write position. So this is metadata. So we have entries in the queue which are metadata entries, which are not visible to the user normally. However, so for example, there's also an index used for finding entries quickly. Because we can have multiple indexes as the file grows, we've got a thing called an index to index. So there's two levels of lookup to find an entry. And finally, we've got the entry that was actually added. So you can see that it's new order single, but you can also see that the sender, the time, and the symbol were actually all integers or longs in terms of how they were actually stored raw. So this tool, dump queue main, has no knowledge of the file or the code or the business logic. This is what it can dump without any special knowledge. Now there's another tool which I should have set up for this demo, which allows you can give it an interface, and it can use the interface and the DTOs to decode them correctly, just as you can see here on the left. It will decode it very similar to this. But as you can see, the sender it appears to be a string, but it's actually a long. The timestamp, again, it appears to be as a long time. It's a microsecond accurate timestamp, but again, it's a long, and the symbol itself is also a long. Now, the header itself is sitting in is actually sitting in shared memory. So this is so what does that mean? So what is happening here is that this program, the one that's writing, and the program that's reading, actually map the same files into main memory at the same time, so that those files are visible to two programs at once. And by making them only a single copy and not making them private, there's actually only one copy in memory of those files. And by using thread-safe operations, we can ensure that they both see the same data at the same time or in a consistent manner. This allows us to essentially have shared memory across as many processes as you have on, or threads on a single machine. That's possible. So the nice feature of that is that another process can see changes as they happen that are occurring in another program. So, so in this case, it's a queue. We have another product called Chronicle Map, which has the same approach. It's a key value store, but again, there's only actually one copy in memory. That copy is visible and equally accessible to every process that's got access to it. None of them have particular priority, and because fundamentally it's just a file, if all of these processes die at once, so these are all exited, those files are still sitting in memory. There's no reason for the OS to just push the files out of memory. So if we restart one of the programs, it's immediately visible. It doesn't even have to load it off disk again. It's already there in memory. This is particularly advantageous when you have very large data sets. For example, in Map, you may have, I don't know, maybe a terabyte of data. That data can be larger than main memory size, but the most recent pages that were used will all be cached in memory, even on a restart. Okay. I think at this point I might open it up to questions.
Okay. Yeah, we've got a few in. Firstly, is a more general question about Chronicle and our stack. How do we deal with market data conflation? For some systems, we're not interested in processing every tick.
Correct. So the approach we suggest there is using Chronicle Map, because Chronicle Map will keep the latest value for any particular key. So that's your starting point. It's Apache to open source, so it's a good start, partly because it's free. However, we do have a product that's specifically designed for Market Data Distributor, which is written for Java and C++, and it can share data between them. So you can have a C++ producer and a Java consumer, and it supports concurrent access to market data. So what does that mean? Well, a concurrent map works very similarly to concurrent hash map in the sense that it has segments. An entire segment gets locked when it's being updated, which means there can't be any readers anywhere in the segment. You can't have more than one writer in a segment either. Whereas Market Data Distributor supports concurrent writes and reads to individual keys. It does that by having essentially multiple copies that it can read and write to for any given key. But when you go to look it up, you're always obtaining the latest, the most recent value written. So that's a more high-performant way of sharing market data across a machine.
Okay. Nextly, you went through kernel/ISO CPU. Any insight you can give on the CPU chosen? Do you have any data on benchmark results by CPU model, e.g. the newest Intels versus Ryzen's?
No, we've not really done enough testing on Ryzen's. If you look at the raw benchmarks, there's about the highest end Intel suggests that the Intels are about 10% faster, 10 to 15% faster per CPU. However, if you look at how you get for your money with a Ryzen and the number of cores that you can get for for even less money, the Ryzen looked very competitive, and I think that will drive Intel to release higher core count CPUs. But even if they do, they're still probably by the end of the year, they will probably have like 64 cores across a dual socket machine, whereas AMD are already releasing a 64 core on a single socket. And probably for less than what the Intel will cost even by the end of the year. So, in terms of higher core count, Ryzen's doing very well. If you look at the raw speed of an individual core, an Intel, especially an overclocked Intel, might have the edge, especially if you don't need necessarily a lot of cores. However, the difference is there's a lot of other factors to consider, things like how is your networking set up, how are you doing TCP upload, how is your disk subsystem set up, and are you getting very good consistent writes, for example. Those sorts of things possibly matter more, but yeah, I can see Ryzen giving Intel more than a run for their money, and if they keep this up, they may well dominate over Intel in terms of the server market in particular, where more cores is an advantage.
Okay. The benchmark accounts for previous JVM warm-ups. Any tips on warming up in a production environment?
Yeah, so getting the warm-up right is harder than it first appears. So the main tip we have is that you don't have to warm up the objects involved. What you need to do is warm up the code involved. So that means that you can create a sort of fake microservice within your application. It can read and write to either fake queues or fake socket connections if your microservice is designed to talk to the network. And it can run through, say, a previous days or hours worth of data. You know, you want tens of thousands of events, ideally, enough events to trigger all the relevant code to warm up. But it needs to be end to end, all the way to the socket connection, if you're going to use sockets, for example. And in that case, you may also have a dummy exchange or something for that socket connection to talk to, so that it can. That might seem like a lot of work, but if you think about it this way, you should probably already have some sort of a pre-production integration test that does something like that anyway and shows that everything works correctly. So really, you're in a way just taking some test code that you had for pre-production and just running it on startup repeatedly until most of the code is warmed up. This, in general, in many cases, it's going to add maybe seconds to your startup time. So it sounds like a lot of effort, but you should be able to reuse a lot of the things you should have done already before you got into production, and not necessarily create a lot of duplicate effort to get this warm up to work. And this is where having some pre-recorded events to process is handy, because you can run a realistic data set rather than a synthetic one. The downside of running a synthetic test, just again and again to make the code warmer, is that you will actually optimize the code for what that synthetic test does, and you may actually be hurting the real case, because that will be de-optimized. That will not be the optimized case, which is why you can't just say, for example, I'll run it internally, but I won't actually write it out to the socket. Just before I get to the socket, I won't write it out. The problem with that is that if your socket code isn't warmed up, you can see delays of about 60 microseconds. It just calling write if the code hasn't actually warmed up yet, and adding 60 microseconds due to on each write, even though that's the last thing you're avoiding doing, is still quite painful. So that's why you really need to go all the way and out to a socket. It just doesn't have to go to the real exchange, right? It can go to your dummy exchange. you think, well, do I need to write a dummy exchange? Well, I would say yes. For your testing purposes, you probably should have a trivial dummy exchange for your code to talk to, so that you can test that it works. Test trades go out to a dummy exchange, for example.
Okay. From your experience, when's it worth using microservices for trading systems? Because monoliths will save you demarshalling and network latency.
That's a good question. So it can save you on demarshalling. However, using microservices can also improve performance. So an example we had was that I had a guy who's actually worked with us before, so he understood Chronicle and he used the techniques previously. But to start with, he wrote a trading system as a monolith, and running it all in one thread, essentially. However, after breaking it out into two separate processes, separate threads, so now he's using the processing power of two threads at once. And he could also see, because now you're tracing every message, you could see what it was doing, and he could realize that some of the activity going backwards and forwards between two pieces of functionality was far more than necessary. He tuned that down, and he reduced the end-to-end latency from 35 microseconds down to 23 microseconds. So by adding in a separation between, so it's only going from 1 to 2, but by adding in a separation, he actually sped it up rather than reduce it. So one of the things to consider is that there is a marshalling and demarshalling cost, but there's also a cost in passing objects between threads on different cores. And what we're doing is we're writing that data sequentially to a cache, which is nice and easy to read. It's all continuous in memory. Whereas if you pass an object reference over, and that object reference in turn refers to an array, and that array turns to a whole bunch of objects, and those objects in turn contain strings, and those strings contain char arrays, there's a lot of dereferencing, a lot of cache messing going on to try and get all the pieces of information out of that object. Whereas if it's all been serialized and deserialized, then all of the data that's needed is not only recorded so you can make sure it's efficient, it's all continuous in memory. So when it's passed from one core to another, it can actually be faster than just passing an object reference from one thread to another. Because by the time you access all that data and you pull all the cache lines in. Another thing to consider is that when you pass objects around, or any kind of memory between threads, if it's overwritten, it has to be pulled back in. So the CPU doesn't realize that you're going to override a cache line completely. As soon as you access a cache line, it has to pull it in from wherever it was, pulls it back in, and then modifies it, and maybe overwrites the whole thing, so it can push it back. However, in our case, because we're append only, the cache lines only ever go in one direction, from the producer to the consumers. Those cache lines never get recycled, and so they never get taken back to recycle the memory, because we don't do that. So there is a bunch of reasons why, if you tune this right, you can actually see use cases where it's faster by adding at this level, by making use of more cores concurrently. And you also get obviously a lot more control over exactly how much data is being, what's going on, and how much data is being passed between pieces of functionality.
Great, thanks. Now, I don't want the next answer to this question to be a poor sales organization, but what are the biggest challenges for adoption that people have raised so far? Why isn't everyone using Chronicle? And this follow-up to that is, what is Chronicle's short and medium term with regards to the next frontier that we're tackling, and what currently are the biggest problems that we're tackling?
Yeah, so I think the biggest challenge that we've seen is that this is a different mindset to the way most Java applications are written. So most Java applications are written as end-tier applications, which present some sort of UI interface and have a back-end transactional database. Essentially, we're saying you don't need we don't do any of that. We don't have a backend transactional database. We don't have a front-end GUI either. Instead, it's just computer programs talking to other computer programs. There's a different mindset there, because we also expect these computer programs to respond to enormous amounts of data very quickly. So we're looking at, on aggregate for an entire system, you may be looking at well over 1 million events per second, sort of rates of data you cannot present to a user or even a large number of users. So it's structuring the program differently so that it can handle these very high data rates. And things like transactional databases just aren't capable of handling that kind of writes speed. So that's a lot of the challenges, is getting people to think in terms of real-time event-driven processing, and instead of saying, well, I need a piece of data, I'll just do a query on a database to pull that back in. That would totally destroy your entire budget for how long the microservice should run. So you have to say, well, how do I avoid querying the database for anything? So the answer there is you feed in the data to the microservice. You give the microservice all the data it will ever need as an event coming in, and then it never needs to go somewhere else to get its data. It has everything in its hand. It always needs to respond to things. So it's a different mindset. Another challenge we find is that a lot of systems are really designed to be configured as opposed to developed on top of. And what we largely provide is infrastructure. You can develop on top of that, then that produces the system the client needs. So it's very much a custom application. And they generally clients need to have a number of in-house developers to take it from what we can offer to maintain it for the business use case. Whereas a lot of banks, particularly tier 2 banks, aren't really interested in doing that. What they want to do is have essentially a largely prepackaged solution where they might tweak it a little bit, but for the most part, everything they need to do is through configuration. And that's the sort of challenge we're looking to tackle, is to make our products more configuration based rather than, oh, you could write a little bit of code and it would do this. That's not really the answer a lot of potential clients are looking for. They would rather say, well, actually, I just want to be able to configure it. I don't want to have to write some code. I don't know if I will be able to find developers who can do this reliably. Let's make it a that we have to write code every time we have to add a new piece of functionality, for example.
Okay. So the next one, does Azul Zing give any advantage when running Chronicle-based applications? Will it get worse if one runs non-garbage free code mixed up with Chronicle but using Zing?
Yes, so the one we actually heartily recommend is Zulu, which is another JVM from Azul. That is a supported OpenJDK. And obviously with Zulu, we run just fine. And Azul support back to Java 6, although we don't. We only support back to Java 8. So I have no problem with Zulu. The problem with Zing is that it adds a double dereference to every memory access. And certainly we try to go to some length to reduce dereferencing and jumping around in memory. Most of the applications I've seen using Chronicle don't benefit from Zing. However, it's usually the other way around in terms of when clients engage us. They have usually tried Zing first before they come to us. They'll say, well, we've got an application, let's try Zing to see if it just fixes our problems before we start considering any kind of redevelopment effort. And then they try Zing, and it for whatever reason, they decide that's not sufficient, that they really do need to redevelop something. And then they come to us. the problem with Zing is that it reduces the outliers, but at the cost of making the typical worse, and that's not a trade-off that if you've got the option to rewrite the code, then that's not a trade-off people are necessarily willing to make. If you take, for example, a product like Cassandra, which has a complex life cycle in terms of its data, which means you can't just use the techniques that we do easily, and you can't rewrite the code, well then obviously Zing is a natural choice to run Cassandra, for example, to reduce the impact of GCs. Another thing to note is that a lot of, certainly the way we structure the microservices, the lifecycle of the objects is very simple, which means that we can do some very simple tricks to reduce the amount of garbage produced and recycle those objects, which then means that we're not looking to GC every hour, for example. Ideally, we GC less than once a day. That's no minor collections for a whole 24 hours. And then your choice of garbage collected makes less difference. And in fact, we tend to go with parallel collector rather than concurrent mark sweep, because concurrent mark sweep will trigger in the background whenever it thinks it would be a good time to go off, fire off. Whereas we tend to want to put off doing any kind of collection for as long as possible, in the hope that it can be done only during, say, a maintenance window overnight. And so we tend to use the parallel collector.
Great. Right, this is the last question unless anybody wants to send any more in. Benchmarks are good at development time. What tools are you currently using for product latency monitoring? Oh, sorry, production latency monitoring. Usual stack involving HDR, HIST, Grafana, Influx, or something else?
Yeah, so we have our own histogram called histogram. So it's a bit like HDR histogram. It does a similar thing for reporting. The main trick is the recording of the latencies, and the way we advocate doing that is to record it with the message as it passes through the system, and we have support for doing that. So essentially, along with the message itself, you'll see some trace information as to so basically nanosecond timestamps as it passes through. And that way you can work out when it comes out of the system at the end, you can go back and say, and this is where the source ID was relevant, is you can go back and say, well, at each of these hops between every read and write, where were the delays? Was there queuing? And so on. Then then at the moment, we're looking at a number of different ways of visualizing it. In fact, it's the subject of a later talk, is that one of the visualization companies is 3Forge. Although some clients, what they do is they read the queues and process it and put it into something like Grafana or whatever visualization tool they have. We're also looking at having it more integrated with the trader GUIs so that they can immediately see whether trading with an exchange is performing as desired, or whether there was a delay around a particular trade, which might or may or may not explain why they didn't get a fill or they got a poor fill. So so we do have a talk coming up with 3Forge, which will cover an example. So, in terms of reading the data, it can be read from Java, and then you can process it how you wish. And in fact, we tend to advocate that the queue is replicated to another machine, so that that processing of the reporting isn't actually done on your primary machine to minimize any impact on it.
Perfect. Well, that's the last question. So thank you very much, Peter, for that. As Peter mentioned, the next presentation is going to be in conjunction with 3Forge, and I'll send out the invite to everyone who's registered when we've set that up, which should be in about 2 weeks' time. This has all been recorded, as mentioned at the start, so it'll be available in our LinkedIn Chronicle Performance Engineers group. So once again, thank you very much, Peter, and thank you everyone for your questions and attending. Thanks a lot.
Thank you.
Bye.